Hello students, and welcome back to Chemistry B. I'm Ms. Sleight, and today we're going to be talking about empirical formulas, specifically how you can use mass composition data to determine the empirical formula of a compound. The steps for this process should feel familiar to you because it's exactly what we did to determine the empirical formula of zinc chloride in our lab. First off, as a refresher, an empirical formula represents the lowest ratio of elements in a compound. Now, why does this matter? Well, this is important because of Dalton's law of multiple proportions, which tells us that the same elements can combine in several different ratios to form several different compounds. For example, nitrogen and oxygen can combine to form dinitrogen monoxide, nitrogen dioxide, and nitrogen monoxide. And we need a way to be able to determine if a sample of these two elements, to which compound that sample belongs to. Therefore, we can use mass composition data of a particular sample to determine what its empirical formula is and identify the compound. There are several steps to this process. First off, you're going to need to convert the mass of each element to moles. Secondly, you're going to divide the moles of each element by the smallest element mole amount to find the ratio between the elements. That might seem confusing, but it'll make more sense once we do an example together. And third, you're going to use that ratio to write the empirical formula for the compound. So let's look at an example. In our first example, a compound is composed of 56.0 grams of nitrogen and 32.0 grams of oxygen, and we need to determine the empirical formula. The most important information in this example is the mass of each element, because that's what we need to start with. The very first thing we're going to do here is we're going to convert the mass of nitrogen to moles of nitrogen. Remember, you're going to need to have your periodic table handy to look up the molar mass of each element. So I'll start with my 56.0 grams of nitrogen. I need to convert it to moles of nitrogen. So I'm going to put my moles on the top and mass goes on the bottom, just like a regular dimensional analysis problem. In the case of nitrogen, it has a molar mass of about 14.0 grams per mole. Now we can see that my grams of nitrogen cancel, and I'm left with moles of nitrogen. And when we do (56) divided by 14, we get 4. So I have 4.00, not grams, moles of nitrogen. I'm going to do the exact same thing with oxygen. With oxygen, I'm starting with 32.0 grams of oxygen. Again, I need to convert that to moles. 1 mole of oxygen is equivalent to about 16.0 grams of oxygen. Again, we can see that my grams of oxygen cancel, and I'm going to be left with 2.00 moles of oxygen. Now that was the first step. Now that I've determined the moles of each element, I need to divide to find my mole ratio. Well, oxygen is the smallest, so that's going to be my denominator here. So I'm going to take my 4.00 moles of nitrogen, divide it by my 2.00 moles of oxygen, and that's going to give me a ratio of 2/1. So this compound is 2 parts nitrogen to 1 part oxygen, which means its empirical formula should be N2O. And that's how we determine the empirical formula. So the compound in this sample is dinitrogen monoxide. Our second example says another compound is found to contain 4.20 grams of nitrogen, and 12.0 grams of oxygen. Determine the empirical formula. Take a moment to pause the video and see if you can solve this one on your own. Alright, let's see how you did. So the key things to clue into here is our 4.2 grams of nitrogen and our 12.0 grams of oxygen. So same process as before. I'm going to start with my 4.20 grams of nitrogen and using the exact same molar mass as last time, I'm going to convert that to moles of nitrogen. This way my mass of nitrogen cancels, and then we just need to solve it out. So I would take my .20 grams divided by the molar mass, 14.0, and we get an answer that's going to come out to 0.300 moles of nitrogen. Next up, I'm going to do the same thing for oxygen. Take my 12.0 grams of oxygen, convert it to moles, same way I did in the last problem. Divide by the molar mass for oxygen, which is about 16 grams per mole. When I set it up this way, my grams of oxygen cancel, and then I just do my calculation. So I'd take 12 divided by 16. That gives me 0.750, if we're rounding to sig figs, moles of oxygen. So now that I have my moles of each element, I can divide them to find the ratio. In this case, my moles of nitrogen is smaller, so that's what's going to become my denominator. So I'll take my 0.750 moles of oxygen, divide by my 0.300 moles of nitrogen, and then we'll do the calculation on that. 0.75 divided by 0.3 comes out to 2.5. So 2.5 is a decimal. When we're trying to figure out empirical formula, we really need to rewrite this as an improper fraction. For those of you who don't remember, an improper fraction is one where the numerator is bigger than the denominator. So 2.5 is going to come out to a ratio of 5/2. If you didn't know this one right off the top of your head, I would suggest doing a little guess and check with your calculator to figure out what small improper fraction might represent your decimal number. But now that we have this ratio, we know what our empirical formula is going to be. In this case, our empirical formula is going to be N2O5 because it's 5 parts oxygen to 2 parts nitrogen for this compound, which means our compound in this sample is dinitrogen pentoxide. And that's how you determine the empirical formula for a sample. I hope you have a great rest of your day, and I'll catch you next time.